Okay. Hi, everyone. Welcome to this week's lecture on Monday. I hope everyone had a reasonably restful weekend, or at least productive. The weather was not bad. It wasn't scorching hot, and it wasn't too cold. It was a pretty decent weekend. And I hope you guys were working diligently on your the assignment due this evening. So yeah, as I mentioned, I think last week, I knew we would only be wrapping up sort of momentum topics on Wednesday. And I figured instead of having it due on Friday or Sunday or whenever the old due date was, I figured I'd have it due on Monday to give you a little bit of extra time. However, as soon as this assignment is due, you're going to have to shift gears pretty quickly and start looking into the next assignment because, you know, things snowball pretty quickly. Let's just look at our, before I go much further, the video I was showing in the 10 minutes prior was a sample footage from the SpaceX Dragon capsule launch that happened on the weekend. I think it was Sunday, maybe it was Saturday, I can't remember now. Days are blending together. And that's really exciting for you guys to, you know, be around and old enough to actually remember an actual space launch. I just think that is so cool. I mean, you hear all the time on the radio, or well, no one listens to radio anymore, but you know, on TV and stuff, and how older people are talking about like the Apollo missions. And you know, you guys weren't around then, but you guys are around for this. So you know, in the next 30 years, 40 years, you're going to be talking to your own kids and you know, stuff like that about how you remember the SpaceX Dragon capsule launch, and they're going to think you're old, but you know, you've lived through this. And coincidentally, we also just finished the momentum unit, and we talked about rocket physics and space physics and how they need to use the real Newton's second law, where F net is the derivative of momentum with respect to time. And here we are, you know, just a few days after teaching you that, you're able to actually see live a rocket launch, and you got to see those thrusters kick in, and you saw the second stage of the capsule. So like the big engines kind of got ejected, and they safely returned to Earth. That's what SpaceX kind of their whole business model is, well, among other things. But the big thing they have going for them is the second stage rocket that detached. They were able to bring that back down safely and reuse it for subsequent launches. It saves a huge amount of cost, making space exploration way cheaper. So that's kind of a big thing that SpaceX is pushing. Anyway, so that's really cool. And the other thing we just got finished teaching, I don't know, a couple of weeks ago now, was, you know, forces and gravity and orbits. And one of your midterm questions was Mark Garneau talking to my class last year or 2 years ago. Again, I forget, time is kind of blending together, about how once you're in space, how much easier space physics is. And the midterm question kind of asked you to, you know, explain those a little bit in more detail. I know to the layperson, you might explain to the average person that there is no gravity in space, you know, 0 G is kind of the terminology they use. However, there is gravity in space, right? Technically, if we use physics, Newton's law of gravitation, it's just that there's no normal force. So there's no apparent weight. And I rewinded the video there right at the end because the astronaut there did a sideways backflip, somersault, and to show you kind of how easy it is to do in 0 G. But, you know, that illustrates kind of what 0 G means. It doesn't mean that there's no gravity. It means that there's no G force acting on you, meaning that there is no normal force. Just to put that into context, if you're standing on a floor, there's 1 G acting on you, right? The normal force pushing upwards is equal to the mg down. So, you know, just walking around on day-to-day life, you have 1 G, which is what your brain and your muscles are used to. During launch, you can, you know, you get forces up to like 10 Gs, and, you know, astronauts have to train for that because physiologically, you know, it can make you pass out, or, you know, you can lose blood in certain parts of the body. So, you know, they do have to train for this. And, you know, forces and physics in space they go hand in hand. It's a really cool topic, and I'm really glad you guys were kind of alive to see that. And even if you kind of weren't watching it live, you can always go back And like, there's videos all over the internet and on YouTube and stuff like that. I strongly advise that you go and watch a few of them. They're just so cool. Yeah. Okay. Anyway, moving on. Let's, without further ado, I guess, let's take a trip over to. I have to get my tablet ready here. Let's take a trip over to the course notes. Okay. Scroll up. Okay, so according to the schedule, today we are going to be doing a mixture of momentum review questions and talking a little bit more about explosions. So technically we've covered all this, so there's technically no new information in today's lecture compared to last week. But, you know, practice makes perfect. And I know physics can be challenging to just, you know, show it to students once and, you know, expect students to just, you know, perform in the top tier. And momentum, as I said before, momentum is a pretty head honcho idea in physics. Like everything kind of boils down to the conservation of momentum to some extent. So I think the more examples we kind of do with you, the better it'll be for you guys to sort of retain this content in your brain and understand it and appreciate it and kind of see how it's used. So I think it's a good use of time to spend most of today talking about very, very niche and not niche, but like very specific kinds of momentum problems to really show you the power of how far momentum analysis can take you. Now, before we jump into a question, I mentioned in last week's video there was a really cool demo I do in person, had we actually had an in-person class, where I take two carts and I bash them together in class, and you can kind of see how if one cart is heavier, it'll go through. If one cart is lighter, it'll bounce backwards. However, I tried to get into campus. I'm not allowed into campus yet. I still think things are kind of reopening slowly. So I tried very hard to find a suitable video online. I didn't find one that I exactly wanted, but I found one that was close. So let's take a few minutes, and this will help kind of warm us up a little bit for the following questions. But the following video is going to help remind students. Actually, let me show you here, if you recall. There, we had a chart here where we developed some intuition with collisions, where if we have an elastic collision between an object that's moving and a second object that's stationary, we can develop some intuitions behind what attributes are going to happen after the collision. So we did things like if mass 1 was bigger than mass 2 was bigger than, you know, mass 1, if there's a big mass difference between the two, or if the two are equal. So we went over that chart last week. I think it was on Wednesday. So I'll show you a video now to sort of refresh you on those ideas, and then we're going to jump into some examples there. So let's go back to YouTube, and that's not it. Hold on. I thought I opened it ahead of time. I guess I didn't. There we go.
Today we're going to demonstrate elastic and totally inelastic collisions. I have two carts and a track. The carts both weigh the same amount. Their masses are the same. And they have magnets here that oppose each other. So there's a magnetic force. And so what I'm going to do is leave one stationary and then push the other at a slow speed and see what happens after the collision. So what you can see is that this one that started off moving collided, didn't actually hit it, but the magnetic fields interacted for a very short period of time and transferred all of its energy to the other cart. And we can do the same thing in reverse. It transfers all of its energy to the other one. That's a so-called elastic collision, where there's no energy lost in the collision. During the collision, both energy and momentum are conserved. And when you solve the energy conservation equations and the momentum conservation equations, you find that all of the energy must be transferred from the one to the other. The other way you can do this is in the frame of reference of the center of mass of these two carts. And if I'm capable of pushing them both at approximately the same speed, then they'll hit and leave each other at the same speed that they came together. These carts are different. They have no magnets, but they have some Velcro here and here on both of them that allows them to stick together. So if you start with this one stationary and this one moving, then once they hit, then they move along together at a slower speed than this one was moving originally. This one has 0 energy initially. This one has energy 1/2 mv squared. Once they hit, they move along as a unit with twice the mass and a smaller velocity that you can calculate from conservation of energy. You can also do this one in the center of mass frame. And if you impart the same momentum to this one, equal and opposite momenta to these two, then you can get them to stick and remain stationary. Just like that. That's a totally inelastic or perfectly inelastic collision.
Okay, so wasn't quite the perfect video that I wanted to show you because apparently they just don't exist. But hopefully that allowed you to sort of visualize what I meant when two objects, for instance, of the same mass collide elastically. One object will, after the collision, will be perfectly at rest, which when you look at it, it looks like it's some sort of CGI or something. It looks very unnatural. But the physics is what the physics is. It's pretty self-explanatory there, which I think is just really cool. And it'll impart 100% of its momentum to the other one. And he also showed you an example of totally inelastic collision where the two carts collide, stick together, and then there is no recoil. There's no bounce backwards. They sort of just go through the collision as one unit, and they obviously go slower. Anyway, so let that be a little bit of a refresher for you. You have, I guess, another few hours before the assignment is due. So hopefully these next set of problems will, if you are stuck on something, hopefully the next set of problems will allow you to kind of clear up any misconceptions. So in regards to, I thought this would be a fun question here. The pre-quiz on May 26th, I think that was on Tuesday, if my math is right, I could be wrong. You had to watch a few videos of firing a bullet into a block, and then the resulting collision throws the block upwards. And I mean, the solutions to those pre-quizzes are available for you to double check if you haven't done so already. But I thought it would be a nice little full circle tie-in to go back and actually do a formal question, let's say from a textbook, that relates to those videos that you did, now that we kind of have time to go back and do some questions. So let's do that. Here we see in figure in the 9.59 from some whatever textbook, there is a 10-gram bullet moving directly upwards at 1,000 meters per second and strikes and passes through. So here's the key. It passes through. That doesn't necessarily, by no means does that mean it's elastic. It just means they're not joined together at the end of it. Passes through the center of mass of a 5-kilogram block that is initially at rest. The bullet emerges from the block, moving directly upwards at 400 meters per second. To what maximum height does the block rise after the initial position of sitting on the table? So there's a lot going on there. As is usual with physics problems, every word in the physics problem usually means something. At least if it's coming from a textbook. If it's coming on like an online midterm, I obviously have to put more of a story to it, you know, to make it not as Googleable, because, you know, online midterms, I know people are going to try every which way to get the right answer without actually doing the work themselves. Anyway, so here, let's do a second read, but now without the words, we're just going to read for values. And hopefully if we list values for our brain, it'll make it kind of easier for us to kind of figure out what we need to do. So let's say mass 1, oh, I don't know why I'm writing in red. So mass 1 is, say, 10 grams, and it is traveling at an initial speed of 1,000 meters per second. That is fast. I don't even know how else to describe that other than saying that is fast. Passes through the center of mass, okay, of a 5 kilogram block that is initially at rest. Okay, the bullet emerges from the block traveling directly upwards. So V1 prime equals 400 meters per second. And what maximum height? So we don't know V2 prime. And we want to know what maximum height does the block reach. All right. So we have all of our values, we have the things we're asked for, the words are now no longer a problem. It's pretty obvious that a collision has occurred, and as I mentioned last week, a dead giveaway that momentum needs to be used is when there is in some way a collision, whether it be elastic or inelastic or whatever, there's a collision involved. So that tells me momentum. So I'm going to draw my chart. Well, it's a one-dimensional problem. I don't know if we really need a chart. So maybe I'll say note that this is a one-dimensional problem. So I'll say no chart is needed. Okay. So everything's either up or down. So that kind of makes things easier. So starting with conservation of momentum, I'll say P total equals P total prime. And what's going on before the collision? Well, before the collision, we have the momentum from 1 plus 0, because the momentum of the block is 0. It's just at rest on top of a table, so there's no momentum from the block. And then afterwards, we have momentum 1 prime plus momentum 2 prime. And both of the blocks, both the bullet and the block are traveling upwards. Therefore, they're both positive. So here we say, you know, we let up be positive. Now, everything is traveling up, nothing's traveling down, so everything is positive anyway. Okay, let's kind of start expanding this. We have M1 V1 equals M1 V1 prime plus M2 V2 prime. Okay, what do we have and what don't we have? Okay, so I have M1, I have V1. I have M1, I have V1 prime, I have M2. So the only thing I don't have seems to be V2 prime. So I don't even really need to reread the question. I only have one unknown. So let's just go ahead and solve for that one unknown, because there's really nothing else to do other than to solve for it. So V2 prime is going to equal M1 times V1 minus V1 prime over M2. So that's what the speed of the block will be after the collision. Now, we've solved for something. Maybe that's it. I don't know. Let's go back. So it says, to what maximum height does the block reach? Okay, so they're not asking for V final, but that was the only unknown we had, so we had to calculate for it. So now we have to ask ourselves, we use our problem-solving skills, how does the speed of the block immediately after the collision relate to the maximum height that the block will reach? Now we know from the energy unit that these two are obviously very related. So the next part of the problem, I gotta insert some space here. The next part of the problem is we now have to relate V2 prime to maximum height. So this is me using my problem solving skills, keeping a logical head on my shoulders, a logical approach to the new problem, and you know, relating the speed at the bottom of a hill or a trajectory to the maximum height that it reaches. This is very obviously an energy problem. So we are comparing the total energy just after the collision to the total energy at the top of the trajectory. So let me make this clear. And I mentioned, I think before when we were talking, I think it was on Tuesday, when we were talking about elastic collisions, I said a common mistake is students will mistakenly use conservation of energy during an elastic collision. And that's not true. It's conservation of kinetic energy during an elastic collision. And we did an example later that lecture where we needed to piggyback on conservation of energy. And I said, don't be fooled, I'm not contradicting myself. Well, I'm gonna outline the same thing here. I'm using conservation of energy, but don't be fooled. I'm not contradicting myself. What I'm saying is, this is the conservation of energy between just after the collision to the top of the trajectory. So the period of time between just after the collision and the top of the trajectory is nice and smooth. There's no other events happening. There's no collisions happening in that time. You cannot use conservation of energy between a before a collision and after collision. That's not how energy works. So, but just to reiterate, just after the collision and at the top of the trajectory is nice and smooth. There's no collisions happening there. It's just a flow of energy between one form and another. So that's what I'm doing here. So just after the collision, what types of energy do we have? Hopefully by now we're a little bit more sophisticated. We no longer have to sort of write out the full conservation of energy statement and then sort of systematically cross things off. If you still need to, by all means, go for it. It's just hopefully by now most of us are kind of past that. So I'm just going to intuitively say the only form of energy we have before, like just after the collision but before it rises, is kinetic energy. And then after, once it reaches the top of the trajectory, it's no longer moving, there's no spring, and there's no friction, so the only kind of energy we have is gravitational potential. So we have the flow of energy between kinetic and gravitational potential energy. And now we just do some algebra. We need to relate the velocity to the height. So the question's asking for the height, so let's solve for the height. The height is going to be v squared over 2g. And we know v was over here. So this is going to be m1 squared over 2g m2 squared times v1 minus v1 prime squared. And there you go. There's your final derived equation for the height that the block will experience as a result of having a bullet right through it. Shot right through it. And notice here that my final derived equation has all the variables that are stated in the problem itself. There's no intermediate values, like I swapped out v because we didn't have v2 prime stated in the question, right? So we had to calculate v2 prime with the formula, and thus my final equation has to be in terms of everything given in the problem. Just to be clear, this expectation is universally true in this class. I do try to remind you when you're doing problems, like either in the assignment or on the test, I specifically try to, as best as I can, to say, first give me the equation, then give me the value. But I just want to make it clear, even if I forget to say that, the expectation is still there that you do have your final derived equation. Okay, moving on. We'll just do another fun example. Well, fun. I think they're fun. Hopefully you do as well. A golf ball rolls off the top of a flight of concrete steps. This sounds like a hilarious thing if you actually picture someone at the top of a set of steps pushing a golf ball off of it, but it happens. I mean, it happens with physicists anyway. Gideon, Dan, and I, we've often found ourselves around UTM just, you know, testing fun little things like this. And I've seen some of the other physics profs do this as well. So I know it's not us, it's a bunch of physicists. So that's why they kind of make this wording into textbooks, because physicists totally behave this way. A golf ball rolls off the top of a flight of concrete steps that have a total vertical height of 4 meters. Okay, let me just draw this. Okay, so 4 meters, and we have a golf ball that rolls off. Okay, there we go. The ball hits 4 times on the way down, and each time it hits a stair, it is perfectly elastic. Okay, so it hits 1, 2, 3, and then 4. 1, 2, 3, and then 4. Okay. If the collisions are perfectly, oh, and it says it's 1 meter each time. So 1 meter, 1 meter, 1 meter, 1 meter. Okay, so I guess that sums up to 4 meters. I guess it makes sense that stairs are evenly spaced. Although a 1 meter stair is quite large. I don't know what kind of stairs these are. Maybe they're made for like tall people or giants or something. I don't know. Anyway, if the collisions are perfectly elastic each time it hits a stair, what is the bounce height on the 4th bounce when it reaches the bottom stair? So they want to know the bounce height of the 4th bounce. So they want to know this height. Okay. Naively, what you could do is you could approach this systematically. And you can solve this by doing 1 bounce at a time. Absolutely. That's one way to do it. And if you did that, let's say I asked this question on a test and you did it the way I'm about to outline for you, you'd get full credit, full marks if you did it correctly. But I'm telling you now, the way I'm about to show you is the long way. And then secondly, I'll show you the fast way. So the first way is the long way. You could approach this by solving 1 bounce at a time. So let me just write that down. Solving 1 bounce at a time. Sorry for my messy handwriting. I'm a lefty and this is a frictionless surface. So you put 2 and 2 together, you get messy handwriting, I guess. Okay, so if you want to know the bounce height for the first bounce, you could say something like, okay, conservation of momentum. Something like the momentum before the collision versus the momentum after the collision. So, you know, we could say this is our first collision. So you could say this is going to be mass of the golf ball V before, or I'll say V1, equals mass of the golf ball V prime. And kinetic energy is conserved, right? So I'll say it's elastic. It's elastic. So you could go through the motions to prove this, but because it's elastic, you know that V1 is going to equal V1 prime. Well, I should say they're equal and opposite, right? Because it bounces upwards. So I guess V1 prime is the negative, I should say. It's the negative of V1. But anyway, they're equal and opposite. So just after the collision, the golf ball is going to be traveling upwards with the same speed as it did when it hit. Well, okay, that's interesting. Now we think about if it's traveling upwards with the same speed that it hit, what would the altitude of the bounce be? And we can solve for this using conservation of energy. We can say, well, originally it had gravitational, and then it got converted to kinetic energy, right? It was at rest here at the top, so it had gravitational potential energy, and then when it fell, it gained some speed. So we can actually say that this means that the kinetic energy and gravitational will perfectly interchange. Meaning the bounce height of the first one will be 1 meter. It'll bounce back up exactly to the altitude at which it started from. That's what it means to conserve energy and having an elastic collision. That's like when you dribble a basketball. In theory, when you dribble a basketball, the basketball comes back up to the altitude at which you had dribbled it from. Now, in real life, that's not true, because when you dribble the basketball, it's mostly elastic, although you are losing a little bit of energy due to like sound and friction and heat and stuff like that. But it's mostly elastic. So the first bounce rises up to be the same altitude that it started from. Okay, now for the second bounce, again, this is the long way. If you wanted to analyze this, you do one bounce at a time. The second bounce, it again starts from up here, because that's the end result of the first bounce. And then it would go from here and go all the way down. And again, it would fall. Now it would fall 2 meters. So it would have 2 meters of gravitational potential energy. And those 2 meters of gravitational potential energy will get converted into kinetic energy. And then after the collision, it's again elastic. So it'll have the same rebound speed as what it hit. So it'll actually come back up. Maybe I'll change my color here. It'll come back up to the same altitude and then drop to the third step. And then you can actually keep going with this sort of train of thought, and you're going to get the fact that it will continuously bounce. As long as there's no energy loss, it'll continuously bounce back up to 4 meters, or that initial 4 meter altitude. So the long way is to not realize the pattern and analyze this sort of one bounce at a time. And each time you analyze it, you're going to get an altitude of 4 meters off of the ground. And then by the end, you would just be like, oh, therefore it's 4 meters off the ground, not really realizing the pattern. The shortcut, the second way to do this, is to just realize that if every collision is elastic and no other forces add energy to the system, then this is as if the ball, was dribbled from 4 meters. So it's as if the ball was just dropped 4 meters, and it will bounce back up 4 meters. The key here is that every collision was elastic. So during every sort of striking of the ground, you're not losing any energy. So it can regain all of that energy and take that kinetic energy and resume its original altitude. So that's the key. So this is more of a concept question. This would be kind of like an example of a short answer question on the midterm. You had 2 short answer questions on your midterm. This would be an example of a short answer question, where if you were not so solid on the material, you would be forced to do it the long way and waste a bunch of time. But if you are well versed and well practiced, you don't even have to be like an expert. Just if you're actually honestly putting in the time to do homework and studying instead of memorizing, you should be very easily able to determine that there's a shortcut way to do this. And, you know, that's why the question would only be worth like 6 or 8 instead of like 15 or something, because there's a way to do it using words. You can justify the answer conceptually and not have to rigorously prove it. Okay, moving on. Here is, this was sort of in light of the rocket launch. I thought this would be a cool question because of the SpaceX rocket launch. And although it's not a rocket, like the question isn't about a rocket, the concepts in this question can actually be applied to a 2-stage or a multi-stage rocket. So, you know, I'll talk about that after we do the question once it makes a little bit more sense. So this question here is saying that you have a disc. They call it like a clay disc, which is like, they call it skeet, but whatever. It's like a clay disc, and it's like a Frisbee, and you throw it from the ground. And as soon as you throw it from the ground, let's say, according to the picture, at 25 meters per second at an angle of 28 degrees, whatever, you throw it from the ground like a Frisbee, and it will follow a parabolic trajectory, obviously, because it's just projectile motion, right? It's got a forward velocity carrying it forward, and it's got a vertical component to speed that's subject to gravity. We know this from kinematics, so it usually would follow a parabolic trajectory. Here's the new part, or what I call the fun part. While it's at the apex, or the vertex of the parabola, but the apex of the trajectory, the highest height of the trajectory, you fire a gun or a pellet gun, or you throw a rock at the disc or something like that. You fire an object upwards. In this case, it's the pellet. And the pellet strikes the Frisbee at a certain speed, I guess in this case, 230 meters per second. So I guess it would have to be some sort of bullet, because I can't throw that fast. No one can throw that fast. Now, that collision actually will change the momentum of that Frisbee. And, you know, it'll give it a sort of a kick upwards. So it would have wanted to follow the trajectory downwards, but instead, because of that collision, it gave it an initial kick, or a secondary kick part of the way through its trajectory, and it gave it a kick upwards. So it actually changed or modified the predicted trajectory, and now it's going to travel, after the collision's over, the only force is gravity again, so it's going to go through projectile motion again, but starting at this point. So this is analogous to sort of like a 2-stage rocket, where you have, you know, one type of motion happening for the first so-and-so seconds, or for the first part of the trajectory, and then the first stage of the rocket drops off, which would be some sort of like, you know, collision event. You're changing the mass, and then the second stage rocket kicks in, and then you're modifying the initial trajectory. So anyway, it's very analogous to a rocket launch, I would say. So what are they asking for here? Given everything in the diagram, they're asking for the extra amount of height that is achieved by the Frisbee compared to what the original maximum height would have been. So they're not asking for the overall maximum height, they're just asking for the additional height that was achieved and the additional range that was achieved. Okay, so let's just go through this. Again, new question. Let's just keep our wits about ourselves, all right? I know there's a collision involved, so at some point I'm gonna need to use momentum, at some point. So maybe we just start there. I know there's a collision, so let's analyze the collision here. It looks like there's sort of 2 directions here. So if there's 2 directions, I vote we use the chart. So I'll say, note, this is a 2-dimensional problem. So let's use the chart. So I'm going to have an X component, and I'm going to have a Y component. Okay, and I have 2 objects. So the first object is the Frisbee. Before the collision, the Frisbee is moving 100% in the x direction. It's at the top of the parabola, the top of the projectile motion. We know the vertical component, we know from previous lectures that the vertical component of the velocity will be 0 at the apex or at the vertex of the parabolic motion. So at that very specific moment in time, the momentum of that frisbee or skeet disc will only be in the x direction. So that means it's going to be, oh, I'm still writing in red. That means this is going to be mass of the skeet times velocity in the x direction, and none of it is in the y direction. Okay, maybe I should label this skeet. Okay, before the collision, we have the bullet traveling straight upwards, or pellet, whatever, P-E-L-L-E-T, pellet, traveling straight upwards. We can see from the diagram, that none of it is pointing in the x direction, but all of it is pointing in the y direction. All right, so those are the only two objects that we have in our system. So we're done with the before. So I'm going to draw multiple lines so my eyes can see that there's a difference now between the above two rows and the below rows. Okay, after the collision, what does it say? Does it go through? Do they stick together? Let's see here. They are embedded, so they become one object. So I'm just going to draw a large blob. They become one object. And we know from conservation of momentum that the embedded objects have to in some way be traveling to the right and upwards, right? Because the total momentum beforehand was right and up. So the total momentum after the fact has to be right and up. So in some capacity, we know that the arrow has to be kind of there. Now, I don't know what angle exactly, but I kind of know it has to be pointing rightwards and upwards. So I'm just going to draw some sort of theta here. We don't know what the theta is, but I'm just going to draw it there. So this is going to be, how much of it's in the x direction? It's going to be the momentum after times cos theta. And how much of it is in the y direction? It's going to be the momentum after times sine theta. Okay, now I 100% want to acknowledge something. We still have not really incorporated delta x and h prime into our analysis yet. And I'm only doing that because I'm under the assumption that reading this kind of question is daunting and confusing. So I'm trying to model for you how you as a student who is facing a new problem might approach this, right? We have this sort of algorithmic approach. You always do your momentum analysis. Assuming there's a collision, you always do your momentum analysis and let your results kind of guide what you need to do next. So that's what we're doing. Let's see here. Oh, okay. I want to save some space. I didn't know I was going to delete the whole. Okay, there we go. All right. Now, this helps me obtain my P total x equals P total x prime. And again, we can do the same thing for our y directions momentarily. Ooh, we are running out of space very, very quickly. So let's just add some space here. Okay. So let's write out our total momentum in the x direction. So beforehand is going to be mass of the skeet disk times the x velocity of the skeet disk plus 0 equals mass total v prime cos theta. Okay. And we can do the same thing for P total y equals P total y prime. And this is going to be 0 plus MP, mass of the pellet, times the velocity of the pellet, equals mass total V prime sine theta. Okay, so there we go. Let's figure out what we have and what we need. We have this, we have that, we have the total mass, We do not have V prime. We do not have theta. We have mass pellet. We have velocity of the pellet. We have the total mass. We do not have V prime. We do not have theta. So 2 equations, 2 unknowns. There must be a way to get to an answer, assuming they're not collinear, but we won't go there. All right, so using some algebra, I will, or at least using some algebraic foresight, I'm seeing that the theta variable appears in 2 different ways. It appears as a cos, and it appears within a sine. So solving for theta is going to be difficult. So what we can do is we can use the same trick we kind of did, what was it? There was a previous question last week we did. I forget the exact question offhand, but we can actually say that, you know, P prime cos theta, I can just call it one variable. It's just going to be P prime in the x direction, and this can be P prime in the y direction. And I can actually solve for the magnitude of the components separately, and then use Pythagorean theorem and trig ratios to find the angles as needed. So here I can say that the total momentum after the collision is going to be, again, I just mentioned this Pythagorean theorem, it's going to be the x direction's momentum squared plus the y direction's momentum squared, all square rooted, right? The Pythagorean formula for a right triangle. And we actually know what these are. If we look at our equations here, we see that the momentum in the x direction prime, this thing, is going to actually equal that, msvx. So this is going to be mass of the skeet, velocity of the skeet in the x direction squared, plus, and then py prime. What was py prime? Py prime is equal to this. So this is going to be mass of the pellet, velocity of the pellet squared. All right. And that gets you, well, that'll get you something. I'll keep it as a formula for now, but that'll get you the total momentum. Now, once you have the total momentum, where does that get you, right? That's really the question of the day here. So once we have the total momentum, we can say that the total momentum is going to be mass total times velocity prime. So velocity prime in the x direction is going to be velocity prime cos theta, and velocity prime in the y direction is going to be velocity prime sine theta. So we can say from here that velocity prime, oh, not double prime, velocity prime is going to equal to mass of the skeet, velocity of the skeet in the x direction squared. So v cos theta is vx, plus mp squared vp squared all over mass total. So we now have a formula for v total, or sorry, v prime. So we can take that and plug it into there, also into here when we need it. Now the question is, what's theta? Now just to kind of reference this again, the diagram that is, we're going to have a new theta value here once the collision takes place. That theta value is going to depend on, you know, the mass of the pellet and the speed at which the pellet strikes. It is not the same theta that we started with. It's not 28 degrees. If I launch a boulder, like a giant boulder at 230 meters per second upward to hit the Frisbee disc, that'll obviously make the whole thing pretty much move straight up. So theta would be almost 90 degrees. So it's very different. That theta value is very different than the 28 degrees that we started with. So to find theta, we say theta is going to be the arctan of the components, py prime over px prime, which is going to be the arctan of mpvp over msvs cos 28. Now cos 28 is really close to the cos of 30, and cos of 30 is root 3 over 2. So if you want, you can sort of approximate this to the arctan of mass pellet v pellet over mass skeet velocity skeet. And again, cos 28 is really close to cos 30. Cos 30 is root 3 over 2, so root 3 over 2, just to make your calculations a little easier. So now that we have theta, we can go back and calculate cos theta and sine theta. Now, another math trick to avoid all of the arctan and all of this stuff, we actually know what cos is, right? Cos is going to be adjacent over the hypotenuse, and sine is going to be the opposite over the hypotenuse. So really, what you can say here is you can say the velocity prime in the x direction is v prime. We just calculated v prime over here, so we have v prime. And instead of saying cos theta, where theta is the arctan of whatever, we know cos theta is going to be adjacent over hypotenuse. So we can actually say it's going to be the momentum prime in the x direction over the total momentum, right? Because this is going to be adjacent over hypotenuse, which is exactly what cos theta is equal to. The only reason why I'm showing you this is because, for one, it's simpler, and two, this is actually how we get around propagating uncertainties for trig ratios. So I think you will recall in your lab 2 and maybe even your lab 3, but definitely lab 2, conservation of energy, you would have had a sine theta in there for your delta H. And people were asking me, well, how do I propagate the uncertainty for theta? You don't. What you do is you say, if you need sine theta, then sine theta is going to be, delta H over the hypotenuse, which would be the value from the sensor D. So you can propagate the uncertainty fairly easily now, because now it's a division instead of a sign. Anyway, so we have px, v prime. What's momentum in the x direction? Momentum in the x direction was... Momentum in the x direction was ms vx. So this is going to be ms vx over the total momentum, and the total momentum is that square root business down there. And v prime was the square root business over mass total times ms vx over the square root business, so those cancel. So we actually end up getting ms over mass total vx. That's way simpler. I didn't need a calculator. I didn't get lost in the math. Now I can see that the velocity in the x direction prime is going to be the initial velocity in the x direction times the ratio between the mass of the skeet and the total mass. This is nice and simple. You can see the relationship between the variables. It's quite nice and wonderful. Also shows you the power of using trig ratios instead of sines and thetas, or sines and cosines. We can do the same thing with the y direction. V prime is going to be that big square root over mass total. Sine theta is going to be opposite over hypotenuse, so it's going to be momentum y prime over momentum total. And momentum y prime was mpvp, so square root over mass total. mpvp over total momentum is that square root nonsense. So those cancel. So here we see that velocity y prime is going to equal to the initial velocity of the initial y velocity of the pellet times the ratio of the mass of the pellet to the total mass. Right there. Okay, now that I have the velocities after the collision, where do I go? So now I would say if I'm mimicking what students might feel, I would say I'm perhaps getting a little bit lost in the question. You know, I've done a lot of analysis, I've done a lot of math, I've done a lot of algebra. Where do I need to go from here? So if I scroll up, I just remind myself how much higher H prime does the skeet go compared to its old height. So let's figure that out first. We'll figure out delta x later. So we are running out of room again, no surprise, because it's a long question. So now, to solve for H prime, we can pretend that this is a new object being thrown from ground with Vx and Vy as above. And we can solve for the maximum height this way. So really what I'm saying is we can pretend that, oh, there's two things there. We can pretend that we have this object, let's call it mass total, as being thrown with an initial x component of Vx prime that we calculated above, and an initial y component velocity, Vy prime, that we calculated above. We have those initial conditions, and there's inherently going to be a trajectory that follows this. And we want to know the maximum height of this trajectory. So really what we're doing is we're sort of restarting the analysis. We're saying the point at which they collide is now sort of like the initial point for the new analysis, analogous to when someone just throws something. So now we are thrown back 100% into kinematics. The momentum's over, everything else is over. Now we can just go into kinematics. Actually, we know energy. We could also use energy. Energy is actually a little bit simpler. So if we use energy, we can just say that E total has to equal E total prime. So this is at the ground and this is at the top. And at the ground, the only amount of energy is kinetic energy in the, well, specifically in the y direction. Well, actually, no, let's just say kinetic energy. I'll show you how to break that down. And at the top, there's going to be gravitational potential energy, but there's going to be a little bit of kinetic energy left because it's moving forward. So at the bottom, we have the kinetic energy in the x direction plus the kinetic energy, oh boy, the kinetic energy in the y direction. And at the top, we're going to have mgh plus, now at the top, the only amount of energy, or sorry, the only amount of motion is in the x direction. So at the top, we have EKX prime. And we say, well, there's no forces acting in the x direction. So the amount of velocity in the x direction at the bottom is going to be the same as the top. So those just kind of get crossed out. And we are running out of space again. And of course, I have to hit the button twice for some reason, because Microsoft doesn't know how to program things right the first time. Okay, so expanding on what I have 1/2 m Vy squared equals mg h prime. The m's cancel. So h prime is going to equal Vy squared over 2g. And we know Vy squared. Vy squared, what was Vy squared? There we go. V pellet, M pellet over M total. So V pellet squared, mass pellet squared over M total squared times 2G. Oh, the pen is doing something wonky. There we go. So there's your H prime. Maybe I'll write it a little bit neater for you guys. H prime is going to be mass pellet squared, V pellet squared over 2G mass total squared. There you go. Note here how everything in here is stated in the problem. Okay? And it looked dicey halfway through. It looked dicey to be able to carry through with the derivation, but it's only because you would be trying to introduce an intermediate value, right? You're trying to introduce theta, and that's what's going to make that hard. I can't tell you this strongly enough. If I'm specifically asking you for a final derived equation, there will be a way to do it. So like use some psychology there. You know that there's going to be a way to do it. So here I'm showing you the trick. Instead of using sine theta, cos theta, you can use the trig ratios to avoid all of that mess. Okay, that's H prime. That's part A. Part A is done. Now, if we go back, what does part B say? How much extra distance, delta x, does the skeet travel because of the collision? Okay, so let's now solve for well, the range. Let's solve for when this will, well actually, for B, we're running out of room again. Let's solve for the quantities before anything happens. So B, let's solve for H max and range for normal projectile. So for a normal projectile, let's assume the pellet is out of there, there's no collision, it's just someone throwing a disc. Where will it go? So the maximum height, we know, because we've done this many times in the previous unit from energy, from this question, we know is going to be Vy squared over 2G. So the initial speed of the skeet disk is going to be V skeet times sine of 28 squared over 2G. Now, sine of 28 is really close to the sine of 30. So I guess I'm approximating this value just a little bit. I'm only introducing a very small amount of uncertainty here, or error. But sine 30 is a half, and a half squared is 1 over 4. So just to make my math a little bit more simple, I'm going to say that. It's a pretty good approximation. I know it's not a technically correct formula, but it's a reasonably correct formula. Then the range, yeah, you could use the range equation, but don't, please don't. I would just solve this from scratch, please. So the range would be given by, let's see here, Vx times time. Vx would be speed of the skeet times cos 28 times time. And what would the time of flight be? Well, the time of flight would be twice the amount of time it takes to get from the ground to the maximum height, right? So here we can solve for t by saying something like V2 equals V1 plus AT, in the y direction that is. So V2y is 0, V1y, the acceleration is gravity. So we can say the time of flight is going to be V1y over G, which is going to be V sine 28 over G. And that's the time to go from the ground up to the top. So the total time is twice that. Total time equals 2 times this t. So that would mean we're going to get approximately Vs, cos 28 is around the cos of 30. Cos of 30 is root 3 over 2. Times twice V sine, it's around 30. I know it's not exactly 30, but it's close, over G. Sine of 30 is a half, as we've said before. So this is going to be approximately equal to, this is V skeet, there we go. So this is going to be V skeet squared times, these are going to cancel, root 3 over 2G. There we go. I think that's about done it. Okay, so that's the range. That's the range. Approximately the range, with a very, very, very small amount of error. Now, if we want to know how much farther it goes, if we want to know how much farther it goes, then we now have to calculate the trajectory of the second half of the like after the collision, the second half of the trajectory, the modified trajectory after the collision. So we know these initial conditions. We know V1 prime or Vx prime. We know Vy prime. We know those. So it's going to be traveling kind of up this way at V prime. And we know it starts off at an initial height of what is the initial height here? What did we calculate it as? It starts off at an initial height of Vs squared over 8G. Vs squared over 8G. So we know delta dy is going to be Vs squared over 8G. We know the acceleration is gravity. And we know V1y is going to equal to, what was V1y? What was V prime in the y direction? Where did we have it? There it is. Vp times mp over mt. So this is going to be Vp mp over mt. There we go. And we are wanting the range. So that's a fairly simple kinematics question. We have delta dy, we have g, or the acceleration, and we also have the forward velocity, vx as well. So this is a fairly simple standard kinematics problem. And then once you find this R value, to find how much further it goes, you just say delta x equals r prime plus r over 2 minus r. So don't forget, it started out way over here. So this is r over 2. This is r over 2. So this will be delta x. So to find how much farther it goes, you have to say it's the full distance. It's the full distance minus the initial one. So the full distance is going to be, let's see here. The full distance is this. This is what we calculated r prime to be. That's r prime. So the full distance is r prime plus r over 2 minus the initial one, which was just r. So overall, we would say, come on, go sideways. We would say overall, this would be r prime minus r over 2. So we calculated r from before. R was what? Vs squared root 3 over 2g. And then r prime you can calculate here fairly easily. But for the sake of time, because it's already 1220, or sorry, 220, I don't really have time to go through that last derivation there, but it's fairly straightforward. It's a pretty straightforward kinematics question. Okay, moving on. We've got one more question. This one is substantially easier than the one we just did. So if you kind of got lost in that other one, it's understandable. I will actually, let me go back and label something here for you guys, just so you don't kind of feel discouraged. Let me label this as saying, it's likely the hardest momentum problem I could possibly find. Likely. There's a lot going on in there. I mean, could I invent something more complicated? I mean, sure, there's always something more complicated. But I mean, that question there is probably the most complicated momentum question that is reasonably doable for someone in this class. Okay, so full disclosure, I would never ask something this complicated and this involved on a midterm. Okay, that's not the point of a midterm. I know your second midterm is coming up in, I don't know, a week or two or something like that, but I would never ask you something this involved on a midterm, okay? Because that's not the point of a midterm. You've seen the level of difficulty from the previous midterm, right? When I took up the solutions, they were not steps after steps after steps and after steps and substitutions, right? They were pretty straightforward. You know, you draw a free body diagram, F naught equals MA, you do like 1 or 2 lines of algebra and you have your answer, okay? That's kind of what a midterm should be. It's to test a student's ability to, you know, to perform the physics we're teaching you. A question like that I just showed you is kind of pushing the boundary. It pushes you further. You know, if you really study the depths and the nooks and crannies of the power of momentum, then hopefully the easier stuff is, well, easier. You know, it kind of puts things into perspective. So anyway, that's the purpose of that question. The last momentum question that we're going to do today is, again, another interesting application of momentum. And after we're done this question, I'm going to open it up to Q&A before we kind of pivot into something else. Okay, this is listed as like a level 3. I don't actually think it's a level 3 question. It is by no means, it's like, it's definitely not even half as hard. It's less than half as hard as the question we just did, less than half. So if you got lost in the previous question, that's okay. You know, just come back with me and, you know, open up your brain again for some new information. So this is the concept of minimum separation distance. And you know, kind of macroscopically in the big picture of things, when 2 objects collide, you know, let's say one object is stationary and one object is moving. Well, before the collision, they're far apart. During the collision, they're colliding, they're touching, they're deforming. If it's an elastic collision, then the deformations will bounce back and then the objects will regain the initial shapes. But then after the collision, they get far apart again, right? They bounce backwards or something like that. So the question is kind of what happens during the collision? What happens during the deformation process? So really, the question can be asked, what is the maximum deformation? And the maximum deformation is going to occur when the 2 objects stop getting closer to one another. So that's what the notion of minimum separation is. Minimum separation occurs when deformation is at a maximum. And more specifically, in terms of physics, this occurs when the two objects have the same speed. Not the same kinetic energy, the same speed. And if you think about this intuitively, this condition should make sense. This is what I'm saying here, the key idea. The key idea is that the maximum compression will occur when they have the same speed. Please think about this intuitively. Don't just memorize this because I'm telling you. If two objects are colliding, or let's say one is stationary and one hits it from the other side and collides, if they do not have the same speed as each other, one will either get further away or the other one will get closer. And then if it gets closer, then it's not the minimum separation. So when the minimum separation occurs, it's when one object is traveling forward at the same rate the other object is traveling forward. Then the distance between those two objects will not change, hence minimum. So that's the key idea here, is that the minimum separation will happen when the two objects are at the same speed. So with that in mind, let's go into this last question here. A 3 kilogram block slides along a frictionless tabletop. Oh, thank God it's frictionless. I can't deal with another hard question. So at least we're ignoring friction. At 8 meters per second toward the second block of mass 4.5 kilograms. Okay, so far this is pretty good. The spring is on a resting block, fine. We have a spring constant of 850 newtons, that's okay. Part A, what will be the maximum compression in the spring? All right, so let's jump to it. Maximum compression in the spring. We know there's some sort of collision happening. We know the collision is not totally done yet. In fact, in the maximum compression, the collision is only half done, but that's okay because conservation of momentum has to be true at all times, not just before and after, but also during. So what we can start here is we can say that we have momentum total equals momentum total prime. And we can say momentum total is going to be the mass of block 1, let's call this block 1 and that block 2, times velocity of block 1. And then halfway through the collision, when the box is sort of compressing the spring, then the key here is that they're both moving, but they're both moving at the same speed. So this is going to be m1v prime plus m2v prime, but specifically, these are equal because of the key idea listed above. This is not generically true. Please understand, when you have two objects that elastically collide, after the collision is over with, it does not mean the two velocities will always be the same. The two velocities are only the same in this instant because the prime, the after that we're talking about, is specifically halfway through the collision when we're at the minimum separation. So it's a very, very, very specific moment in time. What are they wanting? They're wanting the maximum compression of the spring. Okay, well, we'll deal with that in a second. The only thing we're really able to calculate at the moment is V prime. Oops. So we can say M1 plus M2 times V prime, M1, V1. So V prime is in fact going to equal M1 over mass total. That's a terrible M. Mass total times V1. That's a pretty simple derivation. Right there. Now, to go further, We also know, because we want compression of the spring. So we want compression of spring. So this tells me that there's a transformation of energy that's involved that is needed to be analyzed. We're converting kinetic energy, and we're taking part of that kinetic energy, and we've transferred part of the kinetic energy to the second block, and we've also transformed part of the kinetic energy into spring energy as well. So we say, note that the spring makes this an elastic collision. Yes, you're deforming the spring, but after the fact, if you run this experiment long enough, the spring will, recoil, and the deformed spring will regain its original shape, which is the very definition of elastic. So overall, this will be an elastic collision. The question tells us there's no friction. So elastic collision alone tells us that the kinetic energies are conserved. So that's a relief. We can use that to our advantage as well. And we also have spring energy that's being kind of converted as well. So overall, in this instance, we can actually say that the kinetic energy beforehand is going to equal to the kinetic energy of object 1 plus the kinetic energy of object 2. We know this because elastic collision. But in addition to that, some of the total energy before is also going to be eaten up into spring energy as well. So this tells us, oops, different color, sorry. This tells us that we have 1/2 m block 1 v1 squared equals 1/2 m1 v prime squared plus 1/2 m2 v prime squared plus 1/2 kx squared. All right. Now with this, what do we need? We have v prime actually. We have it from before. So we can go through. First of all, let's just simplify some things. Half, 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 half. Go away. I don't want you. Okay, so where does that leave me? That leaves me with m1. Oh, why am I writing in red? That leaves me with m1 v1 squared, m1 plus m2 v prime squared, v prime squared. So this is going to be m1 squared over mass total squared, v1 squared, okay, plus kx squared. Okay, let's see here. What else can we cancel? One of the mass totals can cancel. So where does that leave me? It leaves me with, why am I writing in red again? m1 v1 squared equals m1 squared over mass total v1 squared plus kx squared. And then the minimum separation, or the compression of the spring, is going to be x equals m1 minus m1 squared over mass total v1 squared all over k square rooted. And there you go. Now, if you wanted to rearrange this to sort of get rid of mass total on the denominator, go nuts. If you wanted to do that, I think another correct rearrangement of this would be, let's see here, it would be what, mass total v1, nope. It would be mass total m1 minus m1 squared v1 squared over k mass total. I think that's another correct rearrangement of what's going on there, I believe. Okay, so that's minimum separation. Like I said, it's far easier than the previous question we did. The only thing you needed to know was the fact that the velocities of the two objects are the same at the point of minimum separation. Okay, we've done a lot of complicated momentum problems. Your brain is probably hurting. So before I take questions, I have a fun little video again to show you. I love doing demos in class, but again, this is not a traditional class. So let me just show you a fun little thought-provoking video. And the video is pretty self-explanatory, but it's pretty cool nonetheless. So let me just show you that. Then we'll kind of shift gears into Q&A, and then we'll do a little bit of center of mass problems before we call it a day. Okay, let me cue up that video for you to give your brains a little bit of a breathing break.
I'm here with Steve Moulder from Britain's brightest BBC One show. Steve, we got you in because we saw something on your YouTube channel involving these boards.
There's about 8,000 beads on the chain. It's 50 meters long and it behaves in this really weird way. They continue to self-siphon all the way to the end and it does this weird extra thing as well. We wanted to figure out what was going on with that and so maybe a slow motion video would help. So the first thing to explain is why does the chain keep going? That's quite easy, really, if you look at it as a sort of tug of war. So you can see here very easily why this bit of chain is winning the tug of war. Because I mean, if in my hand I can feel that it's heavier on this side than it is on that side, right?
Yeah, it's a good weight there.
You can see this is going to be travelling really quickly as it falls, which means this chain here is going to be travelling really quickly as well. And if you've got something travelling really quickly, it's got momentum, right? So you've got this travelling up and it wants to change so that it's travelling down, but it can't do that in an instant because that would require infinite force. Instead, what it does is it changes direction slowly over the course of a loop. So that's why it almost has to be a loop, because it needs that time and it needs that space to change direction. So not only do you get this loop coming out of the pot, but you see waves in the chain as well that seem to be sort of stuck in space, and then you get these corkscrews and things like that. And I think I know why that might be happening. I think it's when parts of the chain strike the rim of the pot, and that sort of knock on the chain travels as a shockwave through the chain. Well, I'll show you what I mean. So if you grab it at the end there.
Okay.
Are we ready to slow-mo this?
Yeah.
All right, here we go. So I'm going to just tap the chain, and you'll see it travels a shockwave, and we'll see it on the slow-mo as well. So that shockwave was traveling quickly through the chain there. But if I was pulling the chain this way at the same time, that shockwave would be stuck. Because it's travelling along, but I'm pulling the chain. So you see it almost frozen in space like that, and that's what you're seeing in the pot sometimes. You're seeing that this sort of almost a corkscrew or waves. Yeah. Here's that corkscrew.
Oh yeah,
isn't that amazing? Yeah. Hopefully, the higher you hold it, then the heavier that chain is. You've got more chain, it's heavier, so it's going to be going quicker. If it's going quicker, the chain on the inside will be going quicker, and the loop will have to go higher. So we should, if we hold it up, get a much bigger loop.
Let's try that.
I'd say that's going about twice as high as it was when I had the pot down here. All I've done is hold it up there.
That loop is definitely bigger. So for me, you know, your theory kind of holds water.
I think it's proof beyond all doubt that I've got that right. Well, no, I think there's still unanswered questions, and we don't fully know what's going on there. So if people have got ideas, you know.
Yeah, absolutely. If you've got ideas, let us know in the comments. You know, what do you think of Steve's idea? Have you got your own theory as to why this is happening? We'd love to hear it.
Okay, so there's a fun little kind of wrap-up video for momentum. You know, we did 2 lectures of momentum. We did this lecture for examples. You know, this is what I love about physics is, you know, yeah, you get these sort of physicsy, you know, personalities that really focus on things that might seem kind of hilarious to the average person. So for instance, like who puts metal beads in a beaker and watches them move? Only a physicist would, okay? But that aside, the great part about physics that I like is you can touch it, you can feel it, you can experience it. So, you know, if you were to just let something fall out of a container, you wouldn't expect for there to be this sort of giant loop that happens. So, you know, that's the sort of recognition of a phenomenon. And then the whole scientific process kicks in. You know, the physicist's brain is thinking, okay, well, there's an unexplained phenomenon. Let me develop a hypothesis. Let me, you know, experiment. I'm going to devise a lab. And, you know, he had a theory that he was testing, his hypothesis. He was testing the fact that the chain was coming down, pulls the chain upwards. So there's an upwards momentum. And then eventually the mass going up eventually travels down. So there has to be a distance over which you slow it down, right? We studied that with stopping a car. We know that there has to be a distance over which things change direction or come to rest. So that's where that sort of extra height comes from. It's the conservation of momentum and the conservation of energy. You can't just instantaneously change the direction of something. And you know, that's obviously the height of this peak is a function of heaviness. You know, the heavier the object, the more distance it will need to change its direction, and also speed. The faster the object, even a light object traveling really fast, is going to need a larger amount of distance to turn around. So, you know, he tested this hypothesis by saying, well, how could I make the chain drop faster? Well, if I hold it higher, we know that it's going to take longer to drop and have more time to be subject to gravity, thus travel faster. So, you know, by holding it higher up, he was able to get the chain moving faster, and faster means more distance to change direction. So I don't know. I just think that whole video was just absolutely beautiful. It really nicely summarizes a sort of scientific method being applied in a very understandable way to a very cool phenomenon that you can touch and feel yourselves if you want to. Okay, so I'm going to stop the recording now. So if you're watching on YouTube, I will see you in the next video. And then after I stop the recording, I'm going to take some questions from the Q&A. Okay, see you all in the recording, I guess, in the next video.